Okay, hello everybody. This is Calc 1 Day 13, Chapter 4, Section 3. We are still in Week 3, and today we are going to look at the fundamental theorem of calculus. Now, the last couple of days, we have taken a look at why we need to use antiderivatives and a little bit of the applications of it. We went through describing the area under the curve and also how we deal with the area if it falls below the x-axis. So today we are now going to take a look at how we can use the fundamental theorem of calculus to make our lives a little bit easier. What the mathematicians Leibniz and Riemann also noticed was there are shortcuts. You can find shortcuts, and the basic premise is, and this is going to seem a little bit redundant here, but if we take the derivative of the integral a to the x of f of t dt, basically we're saying if we take the derivative of the integral, their inverse functions, and we are going to get f of x. Okay, so that would be the derivative. So if we differentiate the integral of f of t, we will get f of x, which is g prime of x. So I'm going to go ahead and start with example 4, just briefly. Looking at example 4 on page 313, you can see that we have the derivative of the integral here of 1 to x to the 4th of secant t dt. So we're going to substitute in our value, and once we do that, we will have secant x to the 4th times 4x cubed by using the chain rule. And the chain rule that we're doing here is because we have x to the 4th, so if we differentiate that, we will have 4x cubed. Okay, so let's move on to example 5 on page 315. Example 5, we have the integral from -2 to 1, x to the 3rd dx. Okay, and we are going to first recognize that the function is continuous on -2, 1. So as long as it's continuous on -2, 1, then we know that we can differentiate it from bigger than -2 to less than 1. So continuous here, and we can differentiate here. All right, now we're going to use what we learned when we looked at antiderivatives a couple sections ago. I believe that was section 3.9. And we use that information to integrate here. So we're going to take x to the 3 plus 1 over 3 plus 1. And we'll get f of x, big F of x, equaling this. Now, what we do next is we're going to use our information that we've learned in the last couple sections to evaluate that between -2 and 1. So, first thing that I do is I substitute in my 1 value, and then I subtract from that my -2 x value. Once I do that, I will have 1/4, plug 1 in, times 1, minus, place -2 to the 4th power is going to be positive 16 over 4. So I now have 1/4 minus 4, which if I place this 16 over 4 and I subtract, I will get negative 15/4. Okay? Notice here we don't have a C value, and the reason we don't have a C value is that we are looking at a definite integral from one end to the other, and if I would add C to this one and subtract C to this one, then they cancel out. So that's not necessary for when you're looking at definite integrals. Okay, and that would be your answer to, that was example 5. Okay, and let's take a look at where they're showing another notation on page 316, and we should probably look at that as well. If we have f of x, big F of x, which means we integrated already, and we have a bracket here, a to b, that would be f of b minus f of a. All right, we're going to take a look at the area under the parabola y equals x squared from 0 to 1. We have looked at this before, but we looked at it using a much longer process. So now we have y equals x squared from 0 to 1. And that would be my area under the curve from 0 to 1, x squared dx. And when I use the antiderivative method, I'm going to have x cubed over 3. And again, evaluating from 0 to 1. So I start with my upper bound, and I have 1 would be 1/3 minus, I plug in my 0, would be 0. So my result of the area under the curve is just 1/3. And that's it. Okay, so let's take a look at example 7. And again on page 316 for those of you that are following in the book. Okay, example 7 says find the area under the cosine curve from 0 to b. Okay, from 0 to b. And we're going to say that b is somewhere in between, well, bigger than 0 because we said from 0 to b, but it's going to be less than pi over 2. Okay, and that's important for our values because, as you know, our periodic functions, we often have some of the same values at different places on the periodic function. So if we have f of x, which we said is the cosine curve, and if I integrate f of x, if I integrate this, I will get sine of x. So my area under the curve will be from 0 to b, cosine x dx equals sine x. And when I plug in my values, I'm going to get sine of b minus sine of 0. Now we know that the sine of 0 is 0. So we find out that whatever my b value is, that's going to be my result. So in particular, if we're taking b, we'll say equal to pi over 2, then we would take a look at sine of, and why am I saying pi over 2? Because I'm looking at my edge here. So if I want to take a look at my edge, and we're looking at the area underneath here, if I want to take a look at my edge, I would say my value of b being pi over 2 was the area under the cosine curve, would be sine of pi over 2, and sine of pi over 2 is 1. So we take a look at figure 9. Here is figure 9 showing my cosine curve coming down, and here's my area under my curve. And if I want to take a look from 0 to pi over 2, I would then just integrate it. And remember, when I integrate it, it's a little tricky to look at because here's the cosine curve, but when I integrate it, I get the sine curve, which gives me my values. So my sine of 0 actually is here, and it comes up this way. Okay, so this is my integration. So that's why I have my sine of 0 is 0, and my sine of pi over 2 is 1, and that's how I get my value of 1. Okay? All right. Example 8 says, what is wrong with the following calculations? So let's take a look at example 8. You can't always just plug and chug and expect that your answers are correct. Sometimes you have to use some wisdom. And here, if I integrate this, I will have x to the negative 1 over negative 1, which would give me negative x to the negative 1. And then when I evaluate that from negative 1 to 3, I will have negative 1/3 minus 1 equals negative 4/3. So I'm thinking, okay, that should be good. But let's take a look at some facts about this problem. First of all, it has to be wrong because the answer is negative, and 1 over x squared is always greater than or equal to 0. So property 6 of the integrals says if you have from a to b of f of x, d of x is greater than or equal to 0 when your f value is greater than 0. So I would have to have the result being positive since I know that this value is positive. So the fundamental theorem of calculus applies to continuous functions, but it can't be applied here because 1 over x squared is not continuous on this closed boundary from negative 1 to 3. Okay, if you recall, it is an infinite discontinuity at 0, so this value of 1 over x squared from negative 1 to 3 does not exist. So we have to be careful and know our functions that we're taking a look at. All right, let's take a look at the fundamental theorem of calculus given to us officially. Again, f has to be continuous on and including a and b. When that's the case, I can integrate it, and then I will find that my derivative of my function will equal my f of x. In order to evaluate it then, after I integrate it using my antiderivative, then I can take f of b minus f of a, where f is any antiderivative of f, and that is if I differentiated that value or that expression after I integrated it, I would come out and get my derivative that I started with. Okay, so again, this is just saying that when you do this, if I can differentiate the integral of f of t, I will get f of x. And this is what shows us that they are, in fact, inverse functions. And wow, that's it. So that is it for today's Fundamental Theorem of Calculus lesson for 4.3. And I will see you in a bit for 4.4.